All right, I want to introduce I want to formalize the process of encryption and decryption, sort of give some of the mathematical formalisms involved. So let me return to the example that we did the very first day of class first. And let me start to introduce some terminology and some cast of characters. The idea is there's always going to be, Alice and Bob want to exchange messages privately and securely. Exchange messages privately and securely. But what I mean is like from a distance, right? So they're like using telecommunications or shouting across some square or something where someone can potentially listen to their communications. And so this example that we had from the first day was that Alice takes so let's just start with Alice, right? So sort of a process here. So Alice encrypts a message, encodes and encrypts a message. Actually, there's two different words here that I want to focus on, encode and encrypt, which mean different things. So, like in our example that we have an alphabet, which you could take as something like, A, B, C through Z, and we even threw in, I think, a hashtag and an @ symbol. And there's an encoding layer where, you send A gets sent to 1, B gets sent to 2, etc. And that you end up in the set, really, now that we have some more math here, we can think of it as the set U29, right? Which is the numbers 1 through 28, but under addition and multiplication. Actually, just multiplication for the purposes of this example. And this is the set of plain text, plain text messages. Let me just a different color for that. They're called plain texts because this is something, I know the text is actually the letters, but as far as the mathematical formalism is going to care about, computers are going to just care about basically numbers or binary sequences of ones and zeros, which we interpret as numbers. Okay, so then we have the encoding, but then what Alice does is she then encrypts. So the encoding is the turning the letters into numbers, right? Something that a computer can read and translate. The encrypting step is actually doing something to the numbers to turn them into something that would look like gibberish. Even if someone knows that like A is supposed to be 1 and B is supposed to be 2, the encryption is turning it into something that looks like a mess. And so the example, what we used was x goes to 11x. That was our encryption function, right? And that gave us, so that's actually, we end up in U29 again. And this is the set of ciphertexts. Is what they're called, sort of the gibberish ciphertext. So just as an example, if we took the letter D here, it would become 4. We multiply it by 11, that becomes 44, but 44 is 15 mod 29. So encrypting D would become 15. Okay, so then, so that's the number that we end up with. Our message is just 1 letter long. I'll talk about longer messages in a moment. So then step 2 is Alice transmits her message to Bob, transmits the ciphertext. It's the ciphertext to Bob, but here's the problem. Eve The third character, Eve, the eavesdropper, is listening in on the line and can intercept the ciphertext. So she can get the ciphertext. Eve can see 15 getting transmitted. Okay. Now, and then, so third, when Bob receives the ciphertext, and he's gonna basically, yeah, he wants to decrypt and decode. Bob receives, decrypts first, and then decodes. So Bob starts with, you know, an element of the set units mod 29, and then there's a decryption function, right? The decryption function, we actually saw last time, or not last time, the first day of class, was you basically send, it's the map x goes to 8x. Because that's what undoes, multiplying by 8 undoes multiplying by 11. 8 and 11 are inverses mod 29. So 8 is 11 inverse in U29. If you multiply 11 times 8, you get 88, which is 1 more than 87, which is a multiple of 29. Okay, so that's decrypt, and that ends up back in U29. And then he decodes. You know, now 1 becomes A, 2 becomes B, and so on, and you get back to the alphabet. Okay. And so he gets the, well, this, yeah, so he turns the ciphertext into the plain text. Right, so the encryption turns the plain text into the ciphertext. Decryption turns the ciphertext into the plain text. Okay, so that's kind of just like the setup there of so just recognize the difference between encoding and encryption. Encoding is just the way we turn semantic messages into numbers. And then encrypting is actually turning a plain text into a ciphertext. Okay, so let me just say what the terminology and the notation is here. So the way people write this stuff down. So the terminology and the notation is the following. You have a couple different sets going on here. You have M, which is a set of plain text messages. You have C, which is a set of ciphertexts. And you have key, which is the key space, a set of possible keys. And I'll explain what a key is in a second. Actually, I can just go back up here and explain this. So like up here, this 11 is the key, right? Because that was that we used to multiply by. So, okay. And so in our example, all of these sets are actually units mod 29. C equals K equals U29, or the way textbooks will say this is F29 cross. Remember, this is the finite field with 29 elements. And the cross means we throw away 0. And we just think about the multiplication. That's supposed to be an F. Okay. That's a Blackboard bold F. Okay, so yeah, so this is our example. Notice the key could have been any number. We chose 11 up here, but it could have been like 7 or 23 or whatever. So that's why the key space is the same. We could choose the keys. So and then so we pick a key. Let me just kind of write some more stuff out here. So we pick a key, little k in the big K set. And then we use that to make an encryption map. Then we get an encryption map. Get encryption map. E sub k. So once we fix k, we get a map from the set of plain text to the set of ciphertext. Right. In our example, let me just say, yeah, in our example, E sub k from U29 to U29 was given by, or defined by, E sub k of m is just k times m, where we recognize that we're reducing mod 29, right? Because we're in this mod 29 set, this finite group. And we get a decryption map. D sub k from the set of ciphertext to the set of plain text. It's supposed to be a C. It's more like a big E. Right, and in our example, D sub k was also a map going, yeah, both sets were U29. And this is defined by, well, we want to undo multiplying by k. So we apply it to a ciphertext by multiplying by k inverse. Right, so k. So k inverse times c. Again, mod 20, everything should be like mod 29. All right, so that's our example. A general, so this is kind of the formalism, is like, you know, in fact, I think the Hofstein Piper Silverman book says that a cipher is actually a 5-tuple. So you get into some ridiculous formality when you get into higher math. It's the 5-tuple M, C, K, E, and D. So E and D are basically these functions. You know, you pick a key, and so you pick a K, and then you actually get this map E sub K. You could think of E as being a map from K cross M to C, where E of K comma M is E sub K of M. Oh, and my C looks a little bit like an E. Right, and then D is also a map from K cross C to M. So like you can really mathematize this so the cows come home if you really want, but yeah. So I could say D is a map from K cross C to M, where D of K comma M is D sub K of M. So, you know, this is almost getting to be too formal, but it's basically, that's kind of like the concept. Right, we sort of know, I mean, right, like here, up here, you know, we could think of this being this E of K M is just multiplying K and M mod 29. Okay, so a couple things to notice in general. Okay, so by the way, this has to satisfy, I guess I should say, which satisfies the following. It has to satisfy that if you take a plain text message and encrypt it and then decrypt it, after, having fixed a key, then you should get back where you start, right? Otherwise, it's not a very good cipher. Bob's not going to be able to decrypt, get back the same message. Yeah, this means, by the way, this means that E sub k is actually a one-to-one map. Sort of prove this. This is D sub k is a left inverse of E sub k. And it turns out if a map has a left inverse and it's one-to-one, it's not hard to prove that. But that's good, right? It's good. We don't want, this is a good fact. We don't want two different plain texts producing the same ciphertext. Okay. Yeah. Okay, now the last thing I want to do before we're going to talk about the role of Eve and what we can sort of assume about Eve, what she's trying to do, and what would help her accomplish breaking the cipher. I'm going to talk about it in a separate video, but I just want to make a few notes about this whole setup, just a few kind of more comments, and then we can get into stuff more. So notes. One, what the math of cryptography focuses on is the encryption and decryption. So sort of mathematical, maybe I should say mathematical cryptography. And by that I mean the math and the security aspects, which we will discuss quite a bit. That they focuses on the encryption decryption layer, not the encoding and decoding. Not on encoding and decoding. That's just some scheme for turning semantic messages into numbers, into a bit string that a computer can read in. And so following that, I guess, yeah, let me just talk about encoding a little bit, because it's kind of the only time we'll really talk about it is right now. I mean, if we try to implement specific algorithms, we might have to, and we want to actually play around with sending messages, which we'll do. We'll want to have some basic encoding out systems, but I kind of want to just talk about it and dispense with it here. So this is encoding and decoding are about how computers translate. I've already said this a couple times, but I just want to write it out. They're about how computers translate semantic messages. Semantic means, it has meaning in it, into a string of ones and zeros, into strings, I guess, of zeros and ones that it can read in. Right, and there are standard ways to do this. It's the letter S. We talked about just doing A equals 1, B equals 2, up through Z equals 26. Most computers are more sophisticated than that. For example, there's Ascii Code, which I don't remember what the acronym stands for, but I think the book says in a footnote. But basically, it translates symbols, or it assigns to each symbol, meaning like upper and lowercase letters, digits, punctuation, all the stuff you can write on a keyboard, into a number, assigns to each symbol a number between 1 and 255. It doesn't use all of those, but between 1 and 255, which is 2 to the 8th minus 1. And so basically this can be then converted into an 8-bit, like an 8, in binary, that would be at most 8 bits, right? A bit is really what a digit is. Digits are 0 through 9, bits are 0s or 1. Which gives this gives an 8-bit binary string. Right, and then what you can do, so our messages, our blocks, basically you're going to take, like in the example that I started with, each block was just, each message was just a one letter, right? And so you could send you basically would send this message letter by letter, in the example we used. But maybe in, with Ascii, you could sort of take, you could convert a long message into a bit string. Into a long bit string, a long sequence of 0s and 1s. And then you can sort of decide, I'm going to just cut it, I don't know, every 200 bits or something, or every 100 bits, or every, I'm just going to cut it into blocks of 100. Cut. Then cut into blocks of a certain size. Like say 100 bits. Even though 8 doesn't go into 100 evenly, it doesn't really matter as long as you cut it into, we could have blocks of 97 bits or 153 bits or whatever. It's just, you can cut it however you want into these blocks, and then we encrypt block by block. And then that's where the math comes in. Decrypt. Block by block. So you encode, however, then you just end up with these, and then you divide your long string up into blocks, and then that's what you're going to encrypt and decrypt. So you can sort of, like we were doing it letter by letter, but you could do it with longer chunks of messages, right? And just maybe just one last point. So that's what the encoding is. That's what's happening with the encoding layer. It's something that's, again, we're not going to talk a lot about in this class because that's not where the interesting math is and the interesting security is. But just as one last point, whatever encryption we choose, whatever encryption, it's really a function, like I said, but whichever encryption method we choose, it should be fast for a computer to turn a plain text into a ciphertext. Whichever, and vice versa. And we'll talk about that later in the semester, about there's some great encryption schemes that just run really slowly. They're very secure, but they run really slowly, and then there becomes practical issues. So whichever encryption, decryption, cipher scheme, cipher we choose, it should, it's only effective if a computer, let me try to write that better. A computer should be able to convert. So we're going to care about the runtime of these things. To convert plain texts into ciphertexts, and vice versa quickly, meaning, using relatively few computer cycles. Okay, so those are the general comments I want to make. But then in the next video, I just want to stop here, but then I'm going to get into Eve's role and how we're going to decide whether something's secure, what some of the real issues we're going to have with different types of ciphers, why even the cipher that we just talked about, besides being very small, is actually a bad choice of a cipher. So I'll stop there and talk about it in the next video.